Thank you for joining today's webinar, Moving Maintenance from Prevention to Predictability, brought to you by RCSoft and Smart Energy International. The energy community is in the midst of a revolution, and whilst the future is bright for consumers, utilities and energy providers face a challenge: the need for increased grid resilience and reliability to support and maintain their evolving grid infrastructure. The good news is that through asset intelligence and predictive maintenance, organizations can reduce profit losses, downtime, and equipment failure, and save man-hours and avoidable expenditure. Taking us closer to this future during today's conversation is Bill McAvoy, Global Industry Principal with RCSoft, and his expertise is well respected in the transmission, distribution, smart grid, and distributed energy resources sectors. Joining Bill is Smart Energy International Editor Claire Beauplain, who will be moderating today's conversation. Without any further ado, over to you, Claire and Bill.
Phil, thanks so much. A very warm welcome to everybody this afternoon, and particularly to you, Bill. Thanks so much for joining us today.
My pleasure.
Before we move on to the presentation, I was wondering if you could perhaps just answer a question for me. Today, we're talking about moving utilities to more of a proactive maintenance program. But how much does IoT play into that process?
Oh, that's a very good question to start off right there with. It plays a lot, and the reason is, as you can imagine, we're going to be talking about condition-based maintenance and different types of approaches to maintenance, which heavily rely on data. So as you can imagine, the more the data is being able to be gathered, the more and better your information will be. But to that point, I also want to talk about, and you'll see a little in the presentation as we talk about the different types of approaches to condition-based maintenance or different maintenance, that it's not only the amount of data, it's the value and the context associated with the data. So as we get into the different approaches, you'll see that having additional data is very important, but also the quality of that data is also going to be critical to success.
The thing is, it's more than just data, isn't it? I mean, there's system integration into your enterprise or corporate-wide systems, and then, of course, the impact on IT/OT integration.
Yes, yeah, those are both actually very good points. As you can imagine, there is, even before IoT came into play as much, there is a lot of data usually available within the various utilities. The issue is that data is usually siloed. So, with recent advancements in the technology and the equipment itself, that is usually these large assets have monitoring capability already embedded in them. Also, there is cheaper sensors that are usually put out when utilities or power, generators are doing some maybe one-off pilots to try new equipment technology. What ends up happening, though, is that that technology and those systems get isolated. So a lot of times there could be 5 or 6 different systems that are out there that have valuable data, but they're not brought in together. To your question on the IT/OT, that happens now because you're seeing the consolidation and integration of systems that have been siloed. They might have been on the OT side to do various functions, and IT now becoming more involved in doing with enterprise strategies, are looking to say, okay, let's bring those OT systems, which are siloed, that data into a central kind of infrastructure point so it can be leveraged across the organization with various stakeholders to do a lot of analytics and various programs.
Well, I'm not going to ask any more questions because otherwise I'm going to completely nullify the need for the presentation. So what I'm going to do instead is hand over to you so that you can talk to us about moving maintenance from prevention to predictability. Bill, the floor is yours.
Oh, great. Thank you. So good morning, all, and thank you. Great afternoon, based on where you are. Thank you all for attending the session. So as we know, energy players are facing major challenges within this rapid changing of the market that's going on. With an increased focus on resilience and reliability, companies need to manage their aging infrastructure efficiency to drive down customer outages and to avoid fines. Through asset intelligence, organizations can reduce downtime, failure, production loss, and with preventive maintenance, it can also help extending the equipment's life and forecasting and predicting expenditures. So in addition, efficiencies can transform your operational costs to be better focused and better used. Today, I'm going to talk about condition-based maintenance and how operational data helps drive maintenance from prevention to predictability. So a couple agenda items I'd like to go through. First, I'll go through some definitions. I'll review terms. Then we'll go through condition-based maintenance itself, what it is, what its value is. I'll review a couple industry use cases in which we've seen lower the total cost of ownership, and also increase the value by leveraging new information and new insight. And then I'll conclude with a summary to go through what the value of all this is. So terms and definitions. So you have RCM, Reliability Center Maintenance, Predictive, APM, PF. You could see them as they come up. Reliability Center Maintenance is the whole program of doing the right maintenance at the right time and the right way. CBM and CM, condition-based maintenance, condition management, are about helping out with RCM, getting more from your processes or your diagnostic data of maintenance plans and programs that are optimize them. When we discuss the broader topic of CBM, condition-based maintenance, or condition monitoring, there are a lot of terms involved. Okay, many of these have a variety of definitions and applications. During today, we're going to focus on condition-based maintenance and more broadly, condition monitoring. Also CMMS, shown here, computerized maintenance management systems. It's a more generic term for maintenance management systems or work order systems that are out there, such as SAP or IBM's Maximo or Cascade, Passport, various enterprise systems that are out there. CPMs typically include integration, as you can imagine, to maintenance management to drive the preventive maintenance down. So we'll talk about this a little bit more in the future of today. So this is a Gartner popular progressive graphic from Gartner and an advisory and research firm. This is intended for a broad use of analytics. While it's mostly true in the IT arena, it's not always as true for OT data and asset management. In some versions of the diagram, the y-axis shows complexity, not value. That's certainly true. Issue is often with the definition of prediction and prescriptive. But with condition monitoring and CBM scenarios, often much of the value is at the lower left. Less complex solutions. The prescriptive or prognostic type implementations are always a ways off. This is in part due to the nature of OT data and what is being monitored. These are engineering systems and components that adhere to the first principles and physics models, not social media, weather, health, etc. So very complex. So now as we move into this is another example of a Gartner. It's called the Hype Cycle. It provides pretty cool insights to most technology innovations. It really doesn't matter what it is. it's based on different types of technology. So it could be web-based applications, it could be big data, it could be outage management systems, distribution management systems. They all follow this very familiar life cycle or adoption cycle. This is certainly true for what's going on with advanced analytics and the promise of things like machine learning and artificial intelligence, which as we go through the presentation today and talk a little more, you'll see that these are items that are very popular and continue to come up within the discussion, especially around condition-based maintenance. So like any other engineering endeavor, it's all about trade-offs in many ways. So while we were speaking of definitions, it's important to understand the maintenance budget and the maintenance type itself. Preventive maintenance, or PMs, are work that is repetitive and prescriptive in nature. It mostly scheduled via time-based schedules and is predefined work. We can create a forecast budget for this that usually is fairly realistic. What actually gets done is a different matter. There's different priorities that come up, different items that might throw that planned work off schedule. Then there are things such as CM's corrective maintenance items. These occur as equipment fails or malfunctions. These are harder to predict, usually incur an impact to the operations team, likely unplanned downtime. It depends on the asset itself on how critical these corrective maintenance items are, but no matter what, they need to be done and corrected based on the impact it could have to operations. CMs and PMs work generally funded from an O&M budget, operation and maintenance budget, although CMs can be large enough that sometimes they can be expensed to what are called capital budgets. Large critical asset replacement work is often a necessary evil in a way. We have to replace and often improve assets when their lifetime is up, or the risk of their failure is too high to continue without replacement. Normally this work is capitalized. In any case, we want to reduce these costs, hence the value, prioritize the work, only do what we absolutely have to lower capital expenditures by extending the asset life and making sure that operations is fully functional. So, what are the benefits as I talk about condition-based maintenance today? As we'll see, there's advantages from a financial perspective. We're changing the cost profile or how the maintenance budget is allocated. We move preventive costs to a mix of calendar and condition-based strategies, which tends to lengthen the maintenance cycle between preventive activities. From a corrective maintenance perspective, some of the reactive maintenance becomes more planned maintenance, improving operations while lowering overall corrective maintenance costs. And finally, from capital expenditures perspective, the capital budget is lowered by more focused capital expenditures and fewer catastrophic failures. From an organizational standpoint, it's typical to find From an organizational perspective, it's typical to find a number of other benefits, including capturing some of the expertise of our best experts with algorithms, responses before we lose those critical employees and that organizational knowledge to maybe retirement or moving on. Asset condition can help with the asset prioritization. With it being easier to access information about assets through one UI, we can also come to decisions quicker in regards to the asset. You are right now performing preventive maintenance on those assets using calendar-based approach. As we look at leveraging data, lowering total cost of ownership, and moving program to a more maturity level, we want to move away from the model where you perform maintenance on an asset like every 6 months, every year, and become more effective and efficient to improve our asset ability. This could be done by using condition-based maintenance. As you can see, we move from reactive up to preventive to condition-based to predictive. And as you can see by the way that the XY axis is working, that the more of the effectiveness of that type of system, the efficiencies come with that. So as we look at condition-based maintenance, it means different things to different people. As we talk to our customers and often find out when we're speaking to them about CPM, that they're all talking about different types. Condition monitoring, when you're talking about failure detection, condition assessment, preventive maintenance, advanced pattern recognition. It means something to everybody that's a little different. So we want to talk about those as we go forward. So in discussions with our customers when they're considering a CBM initiative, we often hear from them that it's perceived to be a little bit overwhelming. Much of that coming from the organizational issues involved. There's a lot of interaction that needed with various groups. What we do is encourage them, and what I do personally is encourage them to get started and start small. Try something with some critical or key assets that are failing often. Start with the data that's currently available. In other words, it's not necessary to try to go out and put all new specialized equipment. Actually, that discussion we talked about in the opening question is when you look at IoT and silo systems. Continue to improve it over time, realizing it's a journey, not a destination, or rather it's continuous improvement process, and that's very important. Once the technical components are in place and the capability is demonstrated, it's pretty easy to expand, and then stakeholders within the organization will realize it. So now I'm going to go into some examples of condition-based maintenance that we have and talk about those in some detail. So the first is real-time condition monitoring. This one you take and gather raw data and turn it into a condition information. Next, you take and transform the condition information by making sure that it has some details and some actual content around it. So you don't always need an instrument to measure certain key characteristics. Third is you begin to now thinking about those, performing the analytics and developing the rules. So one power generator used analysis to determine vibration of the blades of the turbine based on how the turbine was operated. Accumulated vibration inspection data. Similar to lugging a kind of manual transmission, point being you don't need all instruments to get started. Finally, you have the integration into a common data infrastructure where you take all the various data and then you move that into a point where you're starting to now integrate it into your maintenance management system and driving your maintenance plans. And you can see that where we talked about that a little already and how critical it is to take that operational data, real-time data from all those silos and then put it into a format and then use it with integration into your CMMS. And that is what we consider and what I look at and see best practices of a total CBM condition monitoring solution. So as from that, you can see here's an example of that process being used and the real-time condition monitoring generating what we see here is what's called a watch list. Okay. This example shows a watch list that summarizes the data, highlights various attributes associated with the vibration based on various sensor alerts. As you can see, the alerts are color-coded and also have some additional critical asset information. This information is easily obtained from the asset real-time monitoring equipment itself, along with the addition of maybe some lower-cost environmental sensors for vibration nearer the limit. You can see it's color-coded and prioritized. And then from that, you go to what we like to see is some additional alerts based on using that watch list. You can then take and leverage certain features within the technology that have things like pop-up trend, trend cursors, time manipulation, event comparison. The visualization of key data is very, very critical. Makes it frictionless to transition from just monitoring your data into more of an ad hoc analysis, being able to do some additional details with certain methods and processes such as time manipulation. This is a great step towards doing predictive maintenance as you start doing and leveraging some of these functions. So next is the concept of when you take and drilling down, you also, key step is to use the technology and the data to automatically notify critical stakeholders of when an important event is happening, so that they need to know what's going on, various stakeholders across the organization. These notifications are automatically generated based on various events that are identified within the solution set that you're using, as far as putting advanced calculations or bands that allow you to set the criteria so that when an asset is going outside the band of the advanced calculation that you've put in, that it kicks off a notification, sends that notification out, and then allows that stakeholder to quickly assess the situation, acknowledge that they know the event is taking place. They can also add comments in there so that their colleagues always have what the latest information is. These functions all tied, of course, to a process and procedure that not only is the concept of technology using real-time operational data is critical to the success, but also I want to make sure I reiterate as I go through how technology is enabling these programs, that I reemphasize through all of these programs and throughout this whole session today that process and procedures are very, very important. It's a key foundation for being successful with your program. I know that sometimes creates the most the most pushback, of course, is when you're starting to put in various things that are forcing the organization to follow some discipline, but it is key to success. So next, in physics or any other science, right, theoretical work is said to be from first principle. If it starts directly at the level of an established science and does not make assumptions such as an empirical modeling or different fitting parameters, analytics is all about empirical modeling and fitting parameters. There sometimes is resistance to using analytics along with first principles in the industry and energy industry. In real world situations, however, where past performance does not necessarily always guarantee a known future state, combining analytic modeling to enhance first principle modeling can provide you with possible outcomes with different degrees of confidence. The resulting information will help you make decisions proactively versus reacting to an event that just happened. This is key within our technology and with basic functionalities such as leveraging future data, backfilling historical data, configuring calculations that go to scale. These are all critical functions as far as that approach, and it's a very, very good approach. Here's an example. This is a basic example on how first principles of engineering with analytics was used in regards to calculating the expected heat rate. This is perfect example, real example being used in the industry. As you can see, it has the functionality of taking history data using real-time streaming data and also advanced calculations to be able to give that outcome. That once this is developed, it can be used in and rolled out throughout various liked assets within the environment. So next, this is an example of predictive analytics. But not only does this highlight how predictive analytics comes in as far as calculations and leveraging data, this is an example also of taking that critical data, doing analytics on it, and creating what are called key performance indicators, KPIs. And these KPIs for this example are looking and developed and reviewed around abnormal deviations. So the use of a KPI strategy to find a particularly damaged, this one is to find a damaged compressor valve. This valve was able to be replaced in a planned and controlled manner before any critical damage was done to the overall environment. KPIs are usually created where that they could be managed and monitored throughout the month. A lot of organizations do actually monthly maintenance reviews of critical equipment using KPIs. They usually have embedded within their process and procedures. The best practices is to take various KPIs like this and as a group with multiple stakeholders in them, review them, manage them, talk about what the band is, why they're seeing certain deviations of that band from certain types of equipment. So this is a very next level example of how using predictive analytics, but also organizational processes and procedures and various stakeholders collaborating can take and leverage that data. So now we'll get into equipment failure life cycle, okay, which talks about root cause analysis of like post-mortem failures. They often reveal minor indications that went in the past unnoticed or were below any kind of conventional alarming threshold. The life cycle of a typical failure goes in this way, where you talk about P and F curves and PF intervals. So a common curve, this is a common curve that illustrates the behavior of equipment, right, as it approaches failure, is the P and F curve. So the curve shows that a failure starts manifesting, the equipment deteriorates to a point at which it can possibly be detected. That's P, which is up there. If the failure is not detected, right, and mitigated, it continues until a hard failure occurs, which is F. The time range between T and F, and commonly called the PF interval, is the window of opportunity during which you look for intervention can possibly detect that the intermittent failures and address it. P and F intervals can be measured in any unit associated with the exposure to the stress, like run times, cycles, miles, any type of kind of measurement that has an interval, right? To prevent false alarms, right? Conventional alarms typically set kind of high where there's a confidence that something has gone wrong. Meanwhile, small events which may cause some damage go unnoticed. So that becomes an area where it's constant, as we talked about, trying to make sure that it's optimized. There is the approach for run to failure, right? Mentally puts off issues until they are a real problem. At this problem, it's too late. to take steps to mitigate the damage or take steps, and it actually shuts down the machine. Predict, it is designed to detect, as you can imagine, the smallest onset of disturbances and any variable associated with the asset. This widens the opportunity window, right, allowing you time for corrective maintenance. So that's about the P&F curve. Here's a success story in which this is an example where I label it as a success story in adopting data analytic tools because I feel it is. This is an example of a utility in regards to bushing pot devices on transformers. And an electric utility, they were able to find failing bushing pot devices by identifying some of the erratic voltage measurements. This approach is currently now in production. As part of the program, they have about 255 transformers being monitored. Within this process, they were able to identify 2 failing bushing pot devices at 2 substations within the first year before failure or damage occurred. As you can imagine, this is, if you're familiar with the cost of these type of devices within an electric utility, they're very large assets, very expensive. So the cost savings and cost avoidance was very, very large and very successful. So next, talk a little about condition assessment. Condition assessment involves using multiple indicators of asset health and combining them in a way that you can create a score for the asset, right? In this approach, we usually have a given kind of algorithm for each pair group of assets. This allows us to compare relative scores for each asset within a pair group and to apply these scores across a larger family of assets. This can be used not only in driving maintenance, but work prioritization, also where to apply your capital funds and other decisions related to if you have limited maintenance resources to help prioritize that. Following this kind of hypothetical example for a transformer, we determine the value of each factor, right, which can range from a 0 to 5 in the scoring. Then we assign a weight to each factor. Then sum the results, right, to come up with an asset score. So when we can use a similar approach for criticality or any other assessment where multiple factors are warranted. So the determination of factors is usually up to what data is available, right? And so as you sit and discuss this and do the prioritization, you need to know what data is available. You have to have knowledge of the asset, so you need to have some asset experts or experience regarding that. And then the factors, scoring the factors, their weights tend to evolve and improve over time. So this isn't a one-shot deal. You constantly are optimizing it. One of the things that we see and what we're proud of is that our PI system makes this assessment relatively straightforward, as we can acquire data from a wide variety of sources, and doing the analysis is straightforward in using configuration tools. And we use a lot of templates to configure the algorithm and factors and the scoring of types of equipment based on having such experience in that area and working with many of our customers. So here's a customer success story using condition assessment as the core of their maintenance management process. As you can see, their focus was to achieve reliability, high reliability, but also lowering their maintenance costs. As you can imagine, trying to improve a metrics such as reliability, but also trying to lower the cost to maintain such large assets and many assets that contribute to that metric, that's a challenge. So the next couple slides, I'm going to show you pieces of the solution and that allowed them to achieve this and how they went about it. And as you can see to the right where it lists the results and benefits, as you can see, they're pretty impressive. So I'm going to go through a couple pieces of that solution as we go forward. So here's an example as part of the solution, and we talked about actually in the opening, because there was an opening question about it, which was a very good question based on this is a critical piece of it. It's the consolidation and correlation of data from multiple sources. So as you can see by this chart, there is integration both of IT and OT systems, right? So when you talk about information technology systems and you talk about operational technology systems, also a real key is that from these multiple types of systems that could be siloed off and probably most likely are siloed off, and where the real value comes in is to make sure that you can integrate into a single enterprise data infrastructure, right, that allows to bring all these various systems into an environment where it's not only just raw data. That data has to have some context applied to it, right, so that it's used and can be leveraged consistently. And that also, putting that context to that data from these various sources allows it to be prepped for analytics, right? So, so that when you're doing the scoring that we talked about, that the scoring could be based on different variables, but are also used to be consistent, right? So these variables are not only based on asset monitoring and asset condition using real-time data, it also has other kind of environmental and contributing data points to be used when you're doing the asset health scoring. So you can see financial systems to the right also. So many different factors. So the key, integration, single platform, context to the data, so that it could be prepped and used for doing analytics and scoring. So as we move on for the next phase of that, so after you have that data, you saw the solution, many types of systems and data points that were integrated into this enterprise solution. Now we talk about how putting that context together is applied, and then using some advanced calculations and analytics to develop a critical asset listing with scoring. So you can see this is a list. This is I think around load tap changers, critical piece of equipment. It has a scoring. There's multiple levels of this device out there. The scoring is highlighted based on where that device and that asset or location is that might need attention. So based on this scoring, you can then move on and go to the next level or process in your procedure, which in this case, so you saw the list, it had scoring, it was color-coded, right? It raised attention for further investigation based on the score. Now this slide shows how taking and drilling into the next level of that single asset that was red on the asset list based on their score. Now you can go in and see that there's more detail associated with these load tap changes. You can see that there's a good amount of data actually. There's various factors. What this also shows, and up in the mid left-hand corner, is that it shows what the algorithm factors were used to calculate the score. So that's always good for the stakeholder or the engineer or the maintenance person that's looking at the detail of this one asset and giving them a sense of validation of what the scoring was. You can also see there's tons of other type of data points that individual can use. There's also trending, so that they can take and look at various trends within the focus of that data to make sure that they understand that this wasn't just maybe a one-off event that happened. So now we talked about using various condition assessment data, putting it in with context, putting in a measurement and weighing. From that weighing and that asset health measurement algorithm, you create a list of the various asset families and types that has a score. Based on that scoring, you can dig in deep, look at the next level of detail around that asset and why it has that scoring. Then from that, you can take action. This is the slide that shows that customer that we just showed, the 3 steps from condition assessment, how they did their scoring, their rating, their critical asset list, and then their detail. This shows what that program came up with and their cost savings. Not only the total kind of cost savings, which is a pretty substantial amount over the 13-year period, but you can see the first kind of years as it started ramping up and they optimized and continue to use the program. The savings that they received in their substation O&M, which is operation and maintenance budget, which was one of their key goals. And you can see they also broke their savings, they've outlined them into 3 major categories. So maintenance efficiencies, and then failure avoidance and short-term failure avoidances, which is based on being able to catch that large asset or those assets before they fail and caused any outages or additional damage, which is usually a significant cost avoidance. You can also see that the cost savings also in some short-term opportunities where they looked at what are some maybe overall program investments they can do that will buy them some additional efficiencies as they go through the program. So it's pretty significant. So next, I'm just going to go through condition-based maintenance. This diagram kind of illustrates a more conventional view of condition-based maintenance. In this case, we're taking information about the asset, typically usage-based information. So things that come frequently, say maybe a 1, 4, or 15-second rate. Sending this data into a condition-based management system, centralized maintenance management system. If we sent this data directly to a CMMS, it would overwhelm it. So that's why you take an operational database like Pi that can take those various frequency rates of fast real-time data and put it into an area which allows it to be ready, put together, right? So this typical case here, changing from preventive maintenance from calendar to condition, right, or usage-based. In many cases, this is based on runtimes. So we show compressor runtimes or operations, like breaker operations. You could have start and stop cycles on pumps, or even material process, right, like such as tonnage on a convention, a coal convector bay, right, a belt. So many different ways to take that type of data, make it where it's qualified. In addition, right, so once you have this information, you process it. Now you can create work orders based on that condition, right? So these are considered qualitative or characteristic measures. In this case, if we detected a condition about an asset, right, that required further investigation, something like a troubleshoot notification, or a condition for which we can create an actual preventive maintenance action, we would use this approach, right? So an example may be that we detect high vibration on a motor. We detect that the pump is operating consistently off of its best efficiency point, or a significant, like a differential pressure across a filter, right, or a screen. All these are cases where you'd want to notify maintenance to perform a planned function. Here's an example of, based on that approach, a report that's done on the fly that generates based on critical motors, and it's based on the run hours. So that's an example of how you can take that approach. And it also shows information around when it was serviced. So now we're going to start getting into getting close to the end and talking about the next level of kind of detail, which is advanced pattern recognition, APR, which is an empirical modeling technique deploying algorithms used to detect process anomalies and performance degradation in real time. So APR software uses historical data, tags to create kind of models for past performance. And then you have powerful algorithms that detect subtle changes in equipment behavior over days and weeks and even months before conventional monitoring actually has come in, right? Now, as you see these factors, they include actual data, an expected factor or value. Also developed is usually a tolerance band that is used to identify alarms and attributes that might fall outside the tolerance band that need action. The advantages of advanced pattern recognition, right? It's proven statistical technology that can be used centrally to provide, kind of effective failure warning systems to to the business across, like we see it a lot across multiple energy companies that have diverse generation portfolios. Intuitive, it usually is intuitive graphical representation of the model. Those types of programs are very advanced in that way. Usually easy to set up using because it's easy to set up, it ensures fast road to getting value. It needs to be fast and efficient from the model execution based on the complexity of the model. And it actually supports real-time casual network diagnostics, so it knows and shows you what happens with the network itself. And we're seeing APR becoming more and more popular in the industry. So I have mentioned process data, OT data, time series data in this session today. It is different than IT domain data, but also the systems that the data come from is usually an engineering system or a process system. And there are known natural laws that always hold true, right? In this space, it's been recognized that these two techniques, statistical techniques of process data, but as you can see, these two techniques outlined here, they're both similar approach, which include, usually they have kind of training or simulation model, and then they also have a real-time monitoring component, so they run in both models and both modes. I just wanted to talk about this briefly is because they are well known, they're recognized techniques in the process industry. They've been around for a couple decades. I think they primarily came out of, aviation and space programs. But the technique is used very kind of, I'll say, across many industries, and we are also seeing it used in the energy industry. And actually, this shows an example of that being used in nuclear, how the techniques were used. One example shows identifying issues with CW motors where they were able to prevent the unit from being derated, which is an impact on their ability to run at full load. The second example shows where it actually identified issues with a control card. That control card was able to be replaced and fixed before it actually caused the unit to trip, which is a pretty big deal. So you could see that type of approach was being used in the nuclear. So the other final thing, one of the things I want to talk about in there as we get close is the use of operational diagnostic centers. So, globally, as the replacement and maintenance of the utility infrastructure, is getting important. It's always been important, but more and more focused on it. That's allowing it to upgrade and modernize, right, for the electric network so that it can handle more levels of decentralization, right, as we get distributed energy resources coming on. One of the things that we're seeing is the more and more development of what are called these monitoring diagnostic centers, right? They definitely are showing where they're leveraging all kinds of new asset management techniques and technologies that can improve, uptime, reduce costs, maintenance costs, and actually improve overall asset health. This is where we're seeing as more and more of the infrastructure needs to be upgraded, and the deployment of sensors and additional communications and asset management software is being rolled out. These centers are becoming the center to be able to take and leverage that across the board. So this gets to the discussion of not only using modeling, not only using software, but when you're looking at an overall program, doing processes and procedures, but actually taking it to the next level of having a centralized diagnostic center, leveraging all this great technology and information, and being able to work across the organization. So having an organization and technology focused just on operational diagnostics, key, it's critical, and it's helping to make the major paradigm shift to the next generation of predictive maintenance. And we're seeing this more and more. So the last, I think, item I'm going to talk about is just statistical modeling to predict equipment, right? This is the last approach I want to just talk about. We're getting near the end. So statistical process analysis, right? It leverages existing failure records, right? This could be information received from warranty claims or just data archives and history that you might have. It's driven through kind of an analytic procedure to find, and you develop the accurate model for the failure curves, right? And the new data is compared against those models that were used to identify past events, and then looking at any potential failures. As you can see, this example shows the use of data from 23 sensors taken from 100 different engine failures to develop the model, right? Then using the history data and running multiple test models within Pi, the analytics, it takes, improves out, and fine-tunes the model. Once that's done and you use that history to run through, then the approach, you can put it into operations. This example shows it was put into operations, scaled up to manage over 100 engines that they had within the system. So last thing I'm going to do is just go briefly about the Pi system and how it supports CBM implementations. As you can see, we start with the concept that process all the data from physical assets on the left is acquired, right? All that data from all kinds of various assets are taken, and time series data is collected and historized and made available for condition analysis. We assign context to the individual incoming streams to organize all of this data by or written with context about the asset. We incorporate the feature of templates, right, to make the setup of these assets and the analytics very scalable. So you create a format and template, and then you can leverage it out. And then the whole key is visualization at the end, so that you can create those watch lists, the dashboards, and use that on mobile templates. So this also is used when you update, as you can see to the right, implementation with various systems, your CMMS to create work orders or update meter feed to CBM. So with that, I just wanted to give you, show you a little about the Pi system, and I am done, and I hope you found today value, and looking forward to the future discussions. Thank you.
Given that we have a fairly short amount of time available, I hope that you'll forgive me if I just jump right into the questions that we've received. Unfortunately, we probably won't get to all of them today, but we can at least address some of them.
Sure.
Okay, great. So there are a couple that came in actually even before we started the webinar, and I wanted to perhaps mention those first. And now I am just trying to find them. Sorry, forgive me. Right. Okay. So the one of the questions that came in yesterday was, on what topology of assets is the data-driven predictive maintenance best apply? So on what topology of assets does the data-driven predictive maintenance best apply? And then they've said they're generation assets, network assets, or others.
So my first thought in response to that question would be pretty much all assets, right? But also the way it's asked about best apply, I guess if I had to look at prioritization, it's best applied to, I'll say, and I really don't like using the term best apply, but where we see it applied most and started and prioritized within various types of energy segments is within generation, which are large assets, runtime, where you have the process data available, and there's many different, I'll say, types of components within the plant that it can be, you can monitor those various components and help keep the plant running optimal, because runtime is very, very important. So I guess I would say, I mean, I cover power and utilities. We see it in power as far as generation, usually as a priority, and then second, we see it within utilities, within large assets, within substations such as transformers, equipment that is very costly and critical to keeping the network up and reliability. So usually across energy, power, and utilities within the larger asset families.
Okay, so this is not something that you would use across your entire network. It would be very much based on where the cost of failure has significant impact, either financially or in terms of your service delivery.
Yes, and we do see, it depends how mature the organization becomes once they start. They usually go after the larger assets, but we have customers that are very mature and have been doing this for 10 years and continue to roll it out to different types of devices where they, it might be a lower cost device, but there's many of them, and they see a lot of, they're starting to see failures in various places across the system. So now they'll use that analytics for distribution transformers that are failing, and it might be that they're doing it to find out if it's a different certain type of manufacturer, if it's a certain type of year. So ones that were deployed 20 years ago instead of 10 years ago. So it usually starts with large components that are expensive, but then it could be rolled out, and we do have utility customers that use it for large quantity devices that are throughout the network that they need to pinpoint.
As you said at the beginning, as sensors are becoming less costly, your ability to monitor a variety of elements of your network is completely changing to what it was before.
Correct.
One of the other questions that came in is, how open is the global market to adapt technologies from the UK that have proven results in this area? I'm assuming that means that technology is produced by a UK-based manufacturer.
I think from a global market, I don't think there's any. Personally, I can't say it matters where it was produced. I do see that as the industry is getting so dynamic and there's so many different changes going on in this technology, people are looking for advances in the technology no matter where it's being developed or it comes from. It's a very collaborative area, especially when you start talking about analytics, especially utilities. Utilities are very collaborative, power and generation. So I basically don't see that as an issue based on where the development is. The industry is very collaborative.
One question that I had, I have two more questions if you don't mind, Bill, before we have to wrap up. And the one that I have was, how much human intervention is needed in order to generate work orders or next steps when you are using either a predictive or a condition-based monitoring system? I realize obviously they're not the same thing, but how much human intervention is needed or is recommended in order to get the most out of the system, or is it something that you can automate to a fair degree?
So like any good environment, you need to spend some time up front with the right stakeholders to make sure that the process that's being put in place and the data that's being leveraged to use and set the various bands or notifications or analytics around is done right. But once that is done right and based on the environment you have, you should be able to roll that out very efficient. But just like a house, just like any other structure, just like a energy and substation, the foundation you put in is very important. And once you get that out, like our system has templates, once you develop that for a type of asset, you could roll it out by the hundreds of thousands because you have the core foundation based on a template. So you have to put some time up front, of course, to make sure that the data is there, the quality of the data is going to be right, and the analytics are right. But then you can roll that out amongst asset families very, very fast after that.
Okay. And then, unfortunately, the last question that we have time for today is from Mohammed, and he wants to know why do you rate running hours or running hour-based maintenance as predictive maintenance? He refers to slide 29. A pump which is run for a specific number of hours, defined by preventative maintenance, can still give a useful life if it is not giving vibration or any other symptoms, which I'm assuming are causing alarm. It is only condition monitoring which can determine the requirement for maintenance, i.e. predictive maintenance.
Yeah, I think that's a fair question from Mohammed. I think that the example on slide 29, I think that was a run hour display example that was showing how taking specific data like run hours could be one of the attributes that could be used in addition with, I think there was some other attributes that were shown on that. It's used more as a guidance to show that, and I think I actually said that display could be generated on the fly. So, and it had various other equipment types. So it was showing based on what was shown on slide 28, that you could then do some real-time run reports to look at the next level and then go from there. So I think where Mohammed's question was specific about a type of equipment based on run hours, this was showing that you can bring up run hours on multiple types of components, and it shows the variety of it, so it's an on-the-fly report. And if Mohammed has any additional questions, I'd love to talk to him. He can reach out and contact me. I'd be happy to discuss it with him in more detail.
Great. I was just going to suggest that. So, Mohammed, if that hasn't answered your question, please feel free to drop a question into the Q&A box, and we will make sure that we put you and Bill in touch with one another. Unfortunately, Bill, from my side, this is all the time that we have available today. I wanted to say thank you to you from me and from the team for being here, and also wanted to wish you and all of our listeners from the United States a very, very happy Thanksgiving on Thursday. I hope that it will be a day full of joy and blessings for all of you. So without further ado, Phil, I'm going to hand over to you.
Well, thank you, Claire, and thank you, Bill, for really a very deeply interesting and insightful conversation. Also, thank you to our audience for joining us in today's webinar, and that we didn't have the opportunity to address your questions or thoughts during this session. Experts from AussieSoft will be in touch with each of you who submitted questions through the discussion. This webinar will be available on demand on smart-energy.com And from the Smart Energy International team, we thank you for your participation. Be sure to keep abreast of upcoming webinars on smart-energy.com.